Welcome. My name is Susana Sellesbaez, and I will present you today a Vine-based approach for defining critical infrastructure loads. This is the content that I will discuss through this presentation. It is also depicted on top of every slide, so you know where we are in every moment. In a nutshell, in this thesis I have developed a methodology and applied it to a case study. And this is what I'm going to present to you today. The design of coastal infrastructure requires the analysis of environmental variables that can potentially cause the failure of such structures. And usually, people imagine this infrastructure, such as this port on the right, this beach, and the pier, with really nice environmental conditions. Well, engineers must imagine extreme environmental conditions to study hydraulic phenomena such as coastal flooding, wave overtopping, which is no more than water flowing over a breakwater, and beach erosion. These extreme conditions we also call, in engineering terms, extreme events. These extreme events are characterized by having very small probabilities of occurrence. Usually, these hydraulic phenomena result from a combined action of two or more physical processes, such as waves, winds, and rainfall. These processes can be characterized by variables, which are the ones that we as engineers study. For example, in the overtopping results from a combination of certain variables: wave height, wave period, and water level. And from now on, I will refer to these variables that are relevant to the design as design variables. And because we just saw that these hydraulic phenomena that we want to study depend on several design variables, it seems essential to study the relationships and the dependencies between all these variables. However, current industry practices usually study these variables separately, disconnecting the physical dependencies between these variables from the overall analysis. The objective of this research was to develop a methodology to define design loads, or more generally, design values, accounting for their interdependence. In this way, one can achieve a more realistic insight in these physical processes that are going on. To define design values, we usually perform as engineers three main steps. The first step is highlighted in green, the sampling of extreme observations. In here, we study and select the extreme environmental conditions that I was talking about before. The second step, which is highlighted in orange, consists on the modeling of these selected extreme observations. This is actually done by fitting a probability distribution function. Finally, highlighted in pink, we define the design values, which are nothing more than the actual values that are then used in the design of the structure. It is very popular within the industry to use the concept of return periods as a measure of risk. The return period is usually expressed in years. For example, if a storm has a return period of 100 years, this means that this storm might happen once in 100 years. And it is actually the inverse of the exceedance probability, which is also very used to express the probability of a particular event being met or exceeded. We can approach the derivation of the design values from two very different perspectives. The univariate perspective, where we studied one variable at a time, and the multivariate perspective, where we study several variables at the same time. As you can see in this slide, these approaches have very different notions of the three steps that were defined in the previous slide. If we assume that our design variables are independent, then we perform several univariate analyses. If the variables are dependent, we then perform one multivariate analysis with all of these variables, and we study their dependencies. And as you can see in this slide, the multivariate approach is more complex than the univariate approach. The univariate analysis has been very studied in literature. This flowchart presents the previous three main steps. The input is a time series of the variable in question, in which we have observations, usually with hourly resolution, and for several years, as many as possible. From this data, the most extreme observations are selected, and an extreme distribution is then fitted to the extreme sample. And these two stacks are actually based on the extreme value theory. In the univariate case, there exists a one-to-one relationship between the return period and the design value or return level. And this is actually what allows engineer to go from the fitted extreme distribution to the actual derivation of these univariate design values. For example, this graph presents a certain cumulative probability distribution of a certain variable. If we fix a probability, we can find the value that uniquely corresponds to it. And in this case, for example, it would be this our design value. Extending this procedure and this theory to the multivariate case is not straightforward. Let's assume that we want to study these four variables: the wind speed, the wave period, the water level, and the wave height. So now let's assume that we want to actually study the interdependencies between these four design variables. In the first step, the sampling of multivariate extremes, we can ask ourselves this question: how can we find the most extreme set of joint observations in our data? Let's rephrase. Which of these sets of joint observations leads to the most extreme event? Storm number 1 or storm number 2? Well, there is no universal answer to this question because there is no natural way to order vectors as we do with real valued numbers. And by this, I only mean that we don't know at first hand which storm, number 1 or number 2, is going to be the most harmful to our structure. As we know that, for example, a wave height of 5 meters is more extreme than a wave height of 3 meters. The next step in the multivariate setting is to model the dependence between these four design variables. And for that, we need a multivariate probability distribution. In here, we choose to study the suitability of vine cupulas. I will come back to the vine cupulas and its characteristics later on this presentation. The one-to-one relationship between return period and return value does not hold in higher dimensions. So basically, I was confronted at the beginning of this research with three main gaps: how to sample multivariate extreme observations, how to introduce vine cupulas in the engineering design process to model the multivariate dependencies, and how to define the multivariate design values from these vine cupulas. So in order to answer these gaps, I decided to formulate two main research questions that are directed towards the engineering community. And the first one: how can we use the vine cupula models in the design of infrastructure? And what are the advantages and disadvantages of using a vine-based methodology to derive multivariate design values when compared to a traditional approach where the design variables are considered to be independent? However, the amount of existing vine cupulas, and hence the models to choose from, is huge, so it is completely essential to develop efficient selection strategies. In base of this size issue, I posed a secondary research question that is directed more towards the statistical community. Can we identify goodness of fit for bind copula based on 3 equivalent classes? 3 equivalent classes is the way of classifying regular bind copulas, and I will come back to this concept later on in this presentation. To give an answer to these research questions, I followed the methodology that you can see in this slide. I first studied the theory. Then I used some of this theory and state-of-the-art techniques to build what I called the vine-based methodology for infrastructure design. However, in order to use this methodology in high dimensions, I developed an algorithm for vine copula selection. And finally, I tested the methodology and the algorithm in a typical case study in coastal engineering. But you might be thinking, why would we develop a new method if traditional methods work just fine? Well, what if I told you that by using the vine-based methodology, you could have a better insight on the extreme system and on the risk profile of your structure? This is actually possible because we study the multivariate dependence with vines. Vines are graphical tools for defining high-dimensional distribution functions and model complex dependent structures between random variables. The graphical representation of this statistical model resembles a grapevine, hence its name. This is the graphical representation of a vine in 3 nodes. And by nodes, we mean that in the first 3, we have 3 nodes and represent 3 variables, which are the variables that we study in the engineering practice. As the grapevine, the statistical model is composed by a series of nested trees. These trees contain information on the dependent structure, and this information is kept on the nodes and the edges of the vine. The vine joint probability is then defined via pair copula constructions. That is why you see the word copula and conditional copula associated to the edges of this vine in red. In this case, a copula is a bivariate distribution function that describes the dependence between 2 random variables. The conditional copula also describes a bivariate dependence, but conditioned to a certain variable. Finally, a vine is regular if all pairs of edges that share a common node in tree 1 are joined by an edge in the next tree, T2. Regular vines can be classified by 3 equivalent classes. On the top, we see 2 different regular vines. But if we remove the annotation on the variables, we actually see that they share the exact same tree structure. On the contrary, the figure below, we see an example of 2 non-equivalent trees because they do not share the same structure. Until now, I present to you all the relevant theory. And now I will show you how I used all this theory to build a methodology to define design nodes accounting for their interdependence. This methodology is meant to be general and conceptual. So instead of only using vines, you could use other multivariate probabilistic models. But because I used the vines in step 3 and step 4, I call this methodology a vine-based methodology for infrastructure design. So let's go through it step by step. This figure presents a generic application of the vine-based method, and it's directed towards the end user. You can find this figure in the report on my thesis, where you can see the link below. However, for this presentation, I will present you with a more simplified flowchart of the actual methodology. If we start with step 0, which is the multivariate time series, And in this time series, we have observations of all our variables of interest for several years. From this time series, we go to step 1. And in here, we sample the extreme joint observations. And we get what I call extreme sample. But how do I do that? Well, I defined extreme events as an event that has a dominant variable and concomitant variables. The dominant variable is the most relevant to the actual design, and the concomitant variables are the ones that occur together with the dominant variable. So basically, we first sample the peaks or the extremes for the dominant variable, and we then go to the concomitant variables and we select within the same storm that these peaks happen. For example, we select the maximum value that occurs for all the concomitant variables. And by taking this choice, we know that we keep the dependence between these variables is kept in what constitutes the extreme event. Step 2 is a practical engineering step to ensure that the statistical results are in accordance with the physical knowledge of the system. And I will present examples on this step in the case study. In the third step, we select a regular vine copula to model the extreme joint observations that we previously sampled in step 1. However, as I previously presented, the number of possible models is huge. For example, in 7 nodes, we have over 2.5 million regular vines. So over 2.5 million possible models to choose from. That is why I decided to perform exploratory work on the possibility to define goodness of fit for vine copula. But goodness of fit is a very strong word. So I decided to focus on model selection strategies that use graphical and statistical properties of vines. More specifically on the concept of 3 equivalent classes. This exploratory work led to the development of a smart algorithm for vines selection. In this slide, you can see the algorithm, which is also included in the thesis report with the link below. But for now, I would like to highlight the main takeout lessons. This algorithm facilitates the implementation of regular vines in higher dimensions because it significantly reduces the computational effort. And basically, this algorithm allows the user to test a subgroup of regular vines in n nodes, so with n variables, constructed on specific characteristics of the vines in n-1 nodes, so with one less variable. If we now go back to the methodology, step 4 is actually meant to be the link between the pure statistical analysis and the engineering design process. But as I previously mentioned, in the univariate case, we can fix a risk level and then find the unique value that corresponds to this risk level. However, in the multivariate case, if we fix a probability level, we get an infinite space of possible design values. So I decided to, for now, not to focus on this challenge and actually reverse the process. So first, the design values are imposed based on their univariate return period. And then we select a risk scenario that represents the failure mode of the structure that we are designing for. And then, with the vine copula, we can calculate the multivariate return period. If the design values do not fulfill the risk requirements, then, which is basically set and represented by the multivariate return period, the practitioner can just go back and select other univariate return periods to perform the analysis again. And actually, if the risk scenario represents the actual failure of the structure, this multivariate return period is giving us an indication on the overall risk of the whole structure, and provides also some information on the probability of failure. Until now, I presented the theory and the Vine-based methodology. Now I will apply this methodology to a typical case study in coastal engineering, designing a breakwater in Galveston Bay, Texas. This application is fictional, and it is only meant to be illustrative on how to apply in practice the methodology. In here, I present part of the multivariate time series that I used, with 39 years of hourly observations on the 6 design variables that are highlighted in red. If now we go to step 1, the extreme value analysis, and here we have to firstly define the dominant variable. In this case study, I decided that the wind waves, the wave height of wind waves was the most relevant variable to the actual design of the structure, the breakwater. So this was my dominant variable. And the remaining variables were named my concomitant variables. So for example, if we would find the most extreme value in this part of the data set for the wind waves, which is actually 1.97 meters, we then would select the concomitant values that occur together with this extreme value for the wave height of wind waves. In step 2, we study the bivariate dependence between all pairs of variables in our analysis. This is the engineering step that I presented in the Vine-based methodology. And we first study this dependence with correlations. This figure, for example, presents the bivariate correlations between all the pairs of variables. And it's actually a pretty visual figure where engineers can quickly assess what are the intensity of these correlations. For example, the largest correlation occurs between the wind speed and the wave period of wind waves. And this is positive because it's depicted in blue. For example, here we find a negative correlation between the water level and the wave height of wind waves. All these correlations can be assessed also from a physical point of view. For example, if there is a lower water level, waves can be shoaling more. So that is maybe why this correlation in here was said to be negative. In here, we study also the bivariate dependence with copulas. As I previously mentioned, copulas are bivariate distributions that study the dependencies between two random variables. Step 2, as I said, is a practical step where in here we use the copulas to check the statistical dependence between all pair of the design variables in our study to see whether the statistical results agree with what is expected from a physical point of view. For example, the graph on top. In here we see that the correlation between the wave period of wind waves and wind speed is relatively high. Physically, these variables are correlated because wind generates wind waves. So this is actually a nice result, which reaffirm that we are going through the right path. However, if we focus now to the second graph, we see that the correlation between the wave period of swell waves and wind speed is considerably high. So this result raises a red flag to the practitioner because physically these variables shouldn't be correlated. And here is where, with these results, the practitioner can decide whether to actually go back to step 0 and perform the analysis again to obtain better results at the end. In step 3, I fitted all 23,040 regular vines existing to the data set. And out of all of these, I chose this vine that you can see in this slide as best fit to model my data. And here you just need to know that this is the model with the strongest correlations between the variables in the trees. And also, logically, it represents best these correlations. Before going deeper into step 4, let's assume that the breakwater's failure mode is represented by an end risk scenario. An example of an end risk scenario is depicted below. If this house were to be flooded, then dike 1 and dike 2 would have to break for the house to be flooded. So basically, this failure is represented by the end risk scenario. So the traditional approach, as we said, assumed that the design variables are independent. So then we would perform 6 univariate analyses for each of the variables that we are studying. Then we have the results from the vine-based approach. And it's important to notice that we call the combination of these design values as extreme events in both methods. And we can see them highlighted in blue. Let's compare the outcome of both methods. In the traditional method, all the variables are extreme. That's why they're all highlighted in red. However, in the bind-based methodology, only the wave height of wind waves is extreme because we assume that this was the dominant variable. In the vine-based methodology, we find the remaining 5 concomitant variables, which do not have to be per se extreme distributions or do not have to be characterized by extreme distributions, because those are the values that occur together with the dominant variable and might be that they are more extreme observations than this for these variables. So extreme variables can be associated with return periods, as it is understood in the current engineering practices. However, the concomitant variables cannot be represented by return periods, so we would refer to these design values by achieving a univariate exceedance probability instead of associating them to a return period. As we can see here, the design values achieved by the vine-based approach are much smaller than the ones compared to the ones achieved by the traditional approach. If now we focus our attention in the multivariate return periods, we see that the multivariate return periods are much larger for the traditional approach than for the vine-based approach. So if we would fix a specific return period or a specific level of risk, we would achieve larger values for the traditional approach than for the vine-based methodology. And this might or might not translate in a more conservative design, so more expensive design for the traditional approach, and a cheaper or less conservative design for the bind-based approach. In this slide, we can see the application of both methods to the design of a breakwater crest level. In this research, we only focus on a certain formula that allows the engineer to determine what is the actual height of the breakwater. And this depends on what is called freeboard and the height of the still water level. And this is actually associated to the requirements or limitations on the wave overtopping discharge allowed over the breakwater. So what it was done here was basically simulate many samples from both distributions. So in the traditional approach, we sampled univariately many values from the univariate distributions. And then from the vine copula, it was fitted to our data. We sample again many the values. And then we calculate the crest level for each of these joint set of values that were sampled for both methods. And with this, in our case, 10 million outcomes of the crest level, we calculated the empirical cumulative distribution function for both methods. So we can see here that for a return period of 10 to the power 4 years, we get a larger value for the traditional approach, so where the variables are assumed to be independent, than for the vine-based approach. So these results basically are illustrated in this figure, when we can see the amount of volume saved that would lead with the results that we got on the crest level. And you should keep in mind that this is only applied to one design formula and basically to 3 design variables, which are the water level, the wave height for the wind waves, and the wave height for the swell waves. So you can imagine what would happen if we would apply it for all the design formulas and with more variables. Now that you have been introduced to the vine-based methodology and the theory and how this methodology can be applied in practice, I would like to discuss some points that I found interesting during this research. The first one, from all the steps of the methodology, I feel that step 4, the derivation of the design values, is the one that can lead to more interesting discussions. Because, for example, by imposing the univariate design values, what is the actual advantage from engineering perspective? And then, how would then the engineer use the multivariate return period at the end? My answer to the first point is that by imposing the design values based on their univariate return periods, I'm proposing an approach that is simpler and closer to current industry practices, but still presents the added value of the multivariate return periods of the combination of univariate design values. And by assuming that the selected risk scenario in here represent the actual failure mode of the structure, then the multivariate return period that is computed gives the information on the overall risk of failure of the structure. And then it just becomes a matter of choice whether it is possible or not to modify the design based on experience and knowledge on the structure's behavior. Now it's time to give an answer to the research questions. How can we use vine copula models in the design of infrastructure? Well, vine copula models are implemented in the vine-based methodology to model the statistical dependence between the design variables and to achieve a better representation of the physical relationships between all design variables. With vine copulas, we can actually calculate the multivariate probability of exceedance, or multivariate return period, which gives an indication of the probability of failure of the structure. What are the advantages and disadvantages of using the vine-based methodology to derive multivariate design values when compared to the traditional approach, so the univariate approach? The main advantage is that accounting for the interdependence between design variables provides a more comprehensive description on the physical system acting on the infrastructure. However, the vine-based method is computationally demanding, and its applicability should be evaluated on a case-by-case basis. Can we identify goodness of fit for vine copula based on 3 equivalent classes? Well, some advances have been made that bring the community a step closer to answering this question. For example, the new algorithm that I presented in this presentation. Finally, I suggested this branch of further research. In here, I present some recommendations on how to improve the vine-based methodology. The first recommendation is the tackling of the issue of defining design values based on the multivariate return period. So remember that I told you in the previous some previous slides that I inversed the process. So first, basically, I impose the design values based on the univariate return periods and not the multivariate return period. And I just suggest that maybe it could be a way that it's computationally feasible to define or find the best set of design values, or the ones that are the more harmful to the actual final design. My second recommendation is making the methodology more practical so it can be used in the industry. For example, one could generate a toolbox that computes several images and tables that are more practical and visual and helpful to engineers to select easily the best design values for the structure. Finally, I propose to quantify the impact of the vine-based methodology in the actual design of coastal structures or other type of infrastructure. And in here, I propose to apply this methodology to several case studies and several design formulas and quantify the impact in terms of, for example, the volume saved of material. And then maybe one could make an atlas that has the different design formulas, and then it quickly says to the practitioner if it is worth to so to apply the vine-based methodology, or it doesn't add any extra value in terms of optimizing the design. This is the end of my presentation. I would like to thank you all for my attention. And if you have any questions regarding this presentation, you can always send me an email that you find below.